Very good. Okay, we are set. Good morning, Cycle 25 team, and welcome to yet another, do we call it an episode? Another talk. And today I'm incredibly lucky to have Scott McIntosh with me, Dr. Scott McIntosh, solar scientist, dare I say rebel, amazing guy, and kind enough to actually return my calls to have him come on here and do a little bit of a talk about Cycle 25 predictions, what it holds for us, and how some of the predictions he's doing might not be quite the same as predictions that other people are doing. And that's a good thing. It means science has some diversity here. So Scott, I'm going to turn it over to you. And if you want to sum up and get straight into it, that would be awesome.
Yeah, I can do that. Yeah, good morning, everyone. I believe it's probably morning for most of you. It's 9:39 a.m. here in the beautiful Rocky Mountain West. And today, I have the real pleasure of talking to you. Now, I'm going to give mad props out to Frank, my buddy there, who cajoled me into doing one of these talks for the first time. And my most sincere apologies to any of you that have seen my shtick before. Apologies also that the jokes don't get any better the second time. They're still old and stale. But today I'm going to talk a little bit about Hansel and Gretel and the trail of breadcrumbs that we followed to get to where we got to on Cycle 25. So yes, we've been branded rebels and mavericks and probably a lot of other things laden with expletives by some of our peers, because what we are forecasting, I prefer forecast than prediction, but what we're trying to say is somewhat contrary to what the consensus would have you believe. So I'll get through that as we go on, but I'll pull up my slides and start off with the dead people that I was referring to earlier. All right, so let's see if this works. So I'm going to lose you as I put this into presentation mode, if that's okay. And can I get a verbal that those are coming up?
It looks great.
And so I don't want to spoil it for the people that haven't seen this before, but these are three old dead white guys. Okay. Can you count them? Yeah, there's three of them. No dispute. It's not like counting sunspots. There's no dispute that there's only three of them. Okay. So anyway, our story kind of revolves around them. And I always like to put this in the context of a story. So in literally the work that me and my team and I have been doing over the last 10 years is really standing on the shoulders of a lot of giants and other mavericks. And there's another interesting side story I'll tell if I have time when I get to our own little eureka moment about work that was done in the late 80s. But I'll get there when I get there. But really, giving credit to my colleagues who've participated in some of this work, aspects of this work, and also, to our sponsor, the National Science Foundation. So just have that on there. And here's a little bit of a news flash for you all. If you're not all plugged into what our active region popped up at pretty high latitudes last night. And fired off an X-flare just literally minutes before this cast started. So we talk a lot about an event called the Terminator, or the Termination event, and I'll get through that in a little bit. But one of the indicators that has happened or is happening is an X-class flare. So it's not all the measures, but I'll show you some of the others today. So let's see if I can navigate in my own slides. It's telling me that my network is unstable, which is always fantastic. This means my kids are rising from their pits. But here we go. So why are we here? And here's a contrast for you. So in the upper left panel, that was the solar cycle 25 forecast that was made by a consensus of NASA and NOAA colleagues and others. It was run by NOAA and NASA, but it was really a worldwide endeavor where there were many submissions of proposals for what Solar Cycle 25 was going to look like. And the kind of average consensus approach was that yellow thing in the upper plot. So something that looks very much like the last solar cycle, which itself was about half the amplitude of the one before it. Okay, so a few things to note there, that theorists love to smooth the living crap out of the data because it makes it much easier to fit. Okay, just hold that in reserve for later on because we will come back to that. Okay, and then in contrast, you look at the bottom right-hand panel, and if you can see my cursor, I'm going to go over it. You see our forecast for solar cycle 25 in contrast with that one. And I told the guy that made this plot that actually I think his timing of maximum's off. We think that maximum's going to be sometime mid to late 2023 based on our analysis, but somehow everybody keeps slapping it in 2025. I'm not all that happy about it, but I don't really care. So anyway, so there is the blue is the consensus panel relative to ours, relative also to what a mean solar cycle looks like over the last 270 years or so. Okay, so the challenge, or part of our challenge, is to understand this thing, and this is the magnetic sun. Okay, so this animation kind of lays out what the sun's magnetic field does over decades. And you see the ebb and flow, and as this thing meanders through time, you'll see that it flips polarity. So in one cycle, the blue stuff leads the yellow stuff, and then on the next one, it's the yellow stuff leading the blue stuff, and in each hemisphere, so that's a complex bundle of stuff. That's a lot of stuff. Remember how I said I was going to talk about stuff? That's stuff, okay? Magnetic fields are what it's all about, okay? There was a episode of I guess it wasn't the Twilight Zone, but it was the other one that ran concurrent with the Twilight Zone. And there was a beautiful statement about the magnetic field, and that everything's about magnetic fields. And it's actually more relevant now than it was then, because the magnetic field of the sun can become unstable, erupt, and cause some pretty awesome stuff. And thank goodness to the Earth's magnetic field. That's probably why we're here. So let's get into evolutionary physics or chemistry or biology and stick to the boring stuff about this old dead white guy in the bottom corner of the slide. So the puzzle for us, for me, for my colleagues, and probably one of the quintessential problems in all of astrophysics, although don't tell that to a cosmologist, and then categorizes them as a single object. Don't get confused with this stuff. Hold on, I'm getting some friends. Okay, so the idea is, what is the mechanisms that forms this oscillatory behavior in the sun's magnetic output? So sunspots are the longest cataloged signature of solar activity. The record goes back to Galileo and further back still to Chinese astronomers and astrologers, and for thousands of years, who've had various details of records. But you can go through a whole chronology where, following the work of Galileo, a lot of scholarly and ecclesiastical activity revolved around the cataloging of sunspots. And it took not that long, well, about 150 years, before someone noticed that it was cyclic. That blows my mind. All right, that it was repeating almost every 11 years. From that, it took another 50 years for someone, this guy in the bottom corner of the phone, to have to use the newly developed field of quantum mechanics to identify that sunspots themselves were magnetic. And then another 10 years of dedicated observations about 100 years ago. Actually, the anniversary is coming up not too far away, where he noticed that this polarity flipping was going on. So every 22 years, the sun reversed its magnetic polarity. And just to put that in context, we think the Earth's magnetic polarity reverses every 200,000 years, give or take, right? Nobody actually knows. But put that in context, this huge ball of plasma at the center of the solar system flips its entire magnetic field in 22 years. Now, if that doesn't blow your mind, nothing else will, okay? Because that's freaking huge. Then the other subsequent spots. So somehow that mechanism, whatever does that magic magnetic field flipping, produces the sunspots that we see that drive the space weather, that impacts hardware, that creates propagation for you guys. Without that, you wouldn't have propagation. There's all kind of stuff going on, right? But it's all thanks to the godfather of solar physics down here, George Ellery Hale. Okay, Hale's a genius. I'll leave it at that. I could finish there. Hale's a genius. So what we're actually going to figure out here is one of the things that my team got into was whether or not we were actually able to visualize Hale's 22-year cycle in its entirety, and not just through sunspots. And so I'll get there and I'll wrap it all up at the end. And if I get a chance, I can show you some of the interesting kind of meteorological stuff that we've been doing, where we're actually considering the sun as a large meteorological system to try and figure out the patterns of what it sees, what it shows us, and what we can maybe learn from that. So I'll jump on and we'll talk about recent times now. So we are kind of at the tail end of solar minimum, which means that the sun isn't producing spots. So we'll get a few sporadic sunspots here and there. And on the top panel here, you have the daily sunspot number. So in black, it's the whole sun, and red and blue, it's the north and southern hemisphere, respectively. And you see that, and I'm going to completely ignore this because I'm going to put myself in ostrich mode. I'm going to completely ignore the fact that there's massive wobbles in that data. Those massive wobbles in that data are real. But that's a completely different story. Okay? But again, I said before, I think before the camera started rolling, my friends like to smooth the crap out of those data. So those wobbles disappear. Okay, so that's just an added complication to the physics. But it's actually very telling about what's going on. But I'm not going to really get in there today unless someone really wants to press me on it later on, because I can look back to it. But the idea here is what, and I'm trying to get you to my eureka moment, my literal bathtub moment, right? Sunspot minimum is the time where the sun produces no spots. But what my friends and I did almost a decade ago now was we identified that that wasn't the whole story. And if I drop in this, a cartoonized version of what the Hale cycle looks like. So the blues and the reds represent magnetic polarities, blue being negative, red being positive. This is derived from data that we analyzed the living daylights out of from 2002 when I was just a young whippersnapper to the present day. So I've almost been tracking this stuff for 20 years. That blows my mind. My bald spot is getting significantly larger over that time. But what you'll instantly notice is that even though the sun can't make spots, there are 4 significant magnetic activity bands present around the sun's equator at that time. Now, if you're a physicist, the simplest possible interpretation of that is they all cancel one another, because magnetic fields, according to Maxwell's laws, want to cancel one another if they're of opposite sign, right? One of the eureka moment here is that what we noticed was there was something that happened, and it wasn't in this data set, but there was something that happened in February of 2011 that we noticed in another data set, and I'll get to that in a little bit. And that's when the sunspots of cycle 24 really came to life. So you'll notice that sunspot cycle 24, which is this guy, has a few little breadcrumbs, right? Those are not long-lived spots. They live one rotation, no more. After February of 2011, not only does almost all, let's say 5 or 6 longitudes become active, but the spots that are on, or the active region complexes that develop on them, stay down for a long time. Okay, multiple rotations. And so a sea change happened on the sun that day. I said a day, right? Remember I was saying the staggering thing about a sun reversing its field over 22 years? I might be about to show you something more improbable than that, okay? Okay, so just bear that in mind. But solar minimum in this context is not a time where the sun is devoid of field. The net magnetic field is close to 0. But that doesn't mean that the absolute value of the field is close to 0, right? It is highly structured. And it requires that structure to change for the next cycle to fully bloom, right? And I'm going to use crazy terminology like bloom and wildfire and prairie fire and all kinds of stuff to describe what happens next, right? So minimum ends when the Hale magnetic cycle ends. We call that event the terminator. Our deduction from this analysis, which only went back to 2012 at the time, was that the interaction of Hale cycles, so these magnetic cycles, shapes the sunspot cycle. So in other words, the sunspot cycle is an interference pattern driven by the underlying magnetic activity cycle. That's not rocket science. It's a fairly straightforward deduction. And 10 years later, we think we've nailed it, okay?
So to be a little dense for a moment,
there's no such...
as ham radio guys, think of 11-year solar cycles, and we're kind of locked in that because we're not...
Everybody is, Rod.
Right. And this Hale cycle... So this Hale cycle is essentially a 22, and is it in sync with what we think of as regular solar cycles? How do those two relate?
Well, we'll get to that in a little bit.
Okay, I'm jumping ahead then.
Yeah, my buddies and I joke about being easier to change the canon of Star Trek and Star Wars than to get people to not think about solar activity being driven by sunspot cycles, right? And that's the struggle you're facing. And it gets into work that we've published in recent about how the sun and terminators and solar activity may relate to things cyclic, ocean cycles, for example. Because everyone wants to jam stuff onto the sunspot cycle. But what if the sunspot cycle is not the fundamental mode? It's not the clock you should be looking at, right? Because most physics is extremely elegant, simple. And there's big problems when you force the sunspot cycle onto everything, that it becomes very sloppy and disorganized. However, if you use the Hale cycle as your clock, which is actually something we can measure, we know, the other thing about Sunspot Minimum is tell me when it happened. Go for it. It's decided by a panel of humans, right? Not the sun.
And we're waiting for people to agree. Because we're just
man.
sitting back there as the guys that are hoping to take advantage of this, right?
Oh man, don't get me started. Okay.
Okay, I'll let you carry on.
No, but anything that requires a panel of humans to tell you that it happened, that's not a good thing. Okay. Especially when it comes to this, because everyone has a different opinion. They smooth the data differently. They do all kinds of things. And to me, I've been fighting this uphill battle that sunspot minimum means absolutely zero. Nothing. It has no relevance to anything on the sun not making spots. So, but I might be on my own, joined by about 5 people. Okay. So that's a very solitary spot. But here's the data that led us to our eureka moment. So in watching the data, the thing that I had noticed, if I flip back, you'll notice now that these trails of things, so I've been looking at these things called extreme ultraviolet bright points, and they are literally what it says on the tin, okay? They are tiny, they're not tiny. In the old telescopes, they were tiny. There are a few arc seconds across on the sun's disk, so only a few 100,000 meters across, right? Just for scale, that's tiny on the sun, right? And they're like small active regions. Okay, so they're like sunspot complexes, but in a much compressed scale. And if you know a lot about physics, or if you've thought a lot about physics, there's a lot of multi-scale physics on the sun. And the multi-scale physics is generally governed by convection. And we can maybe get into that later if you're interested in that. But what we basically noticed is that the trails of breadcrumbs here that you see of these small features overlap significantly in time. So if I look at solar minimum times between 2007 and 2011 on this, so if I go back again, so this window in here, those bands, I see 4 bands clearly in the data. Look what happens at the sun's equator on February the 11th, 2011. Do you see what happens? So all of a sudden, inside one solar rotation, the sun stops making bright points at the equator. And it doesn't do so again for a long time. This is not a fluke. Using crap data, well, not crap data. So this is the data on the left side of the panels from an older telescope. That's the one that I was in charge of when I was given this task in 2002. How about you start cataloging these things? You might learn something, my mentor said at the time. Okay. I think he probably knew what I was going to find. So you can see something like the same thing happened in 1997. Although the resolution of the data is not quite as good, so you don't have quite the fidelity. But what basically happens is the sun's magnetic environment, so inside the star, changes like that. And like that in the star is a rotation, so 28 days. Don't believe me? We'll talk about it in a little bit. So what we're basically looking at here in terms of this massive global scale interference pattern is kind of illustrated in this cartoon, right? So again, the red, white, and blue thing is a cartoon driven by analysis of a lot of data. None of it is magnetic. It's all I'm observing are features that are in images, right? So this has been used against us to show that we're barking mad, right? We have no direct measurement of the Hale cycle, okay? We're only inferring that it's there through this repeated behavior that we see. And I'm going to throw more logs on the fire as we go, okay? But hold this animation in your heads. Looks beautifully systematic, right? One goes in, it dies, the next one springs up. One of the pieces of physics that's been invoked, so there's unicorns and magic fairy dust that have been invoked to make sunspots magically appear at 30 degrees latitude. But what if I tell you that the actual trail of breadcrumbs starts back up at 55 degrees latitude, 10 years before those sunspots ever appear? And we can map it uniquely. That's kind of a problem, right? Anyway, so back to my Terminator events. So in September of 1997, and some of you, I don't know if any of you are avid followers of the 10.7 radio flux as a proxy for propagation in the atmosphere, but it's a standard unit proxy for my folks trying to understand how the thermosphere and ionosphere are reacting to solar activity. And in September 97, both, and beautifully illustrated in February of 2011, the sun goes through a step function. So if you look at this data, blah, 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 tonking along, solar minimum, boom, up. Never comes back. Well, it does, but 7 years, 10 years later, same thing happens in 2011. Step function. Sun goes along. And it's what's really interesting is, I'm not going to cover this today. While there is a terminator, there is also something else at the end of the solar cycle that marks the descent into minimum or quiet conditions. That's crazy. My buddy is going to be hung in effigy about that one, probably. because there's only one way to explain it, unfortunately for others. So now we look at Terminator events on a broader canvas. So on the top, here's my beautiful sunspot butterfly diagram, so-called because it looks like a butterfly when you project it on its side. Us solar physicists are really smart, so we call things very much as we see them. Bright points in corona are literally bright points in the corona. And these butterfly diagrams are beautiful. And so what we noticed was in the preliminary analysis that the area of the sun's disk that was covered by dark features, spots, goes through 100 microhemispheres. This sounds like complete garbage, okay? But when it talks along at close to zero, and then all of a sudden the amount of area subtended by dark features goes through 100 microhemispheres and never comes back, okay? So these dotted lines that you see were from our very preliminary analysis, just looking at the area of sunspots. See these vertical dotted lines you can see? If I put them up against F10.7, you see that each and every one of them coincides with a step function in activity. And actually on this plot, you might be able to see the step functions down as well, like this one here in 1994, or the one here in 1984. So now you look at the Hale cycle on this broader canvas. So what I've got are these termination events and the starting points. And so I'm basically bootstrapping my way back in time with what the Hale cycle looks like, okay? So now you've got 1, 2, 3, 4, 5 cycles obeying this behavior, okay? Hold on. So actually, hold on. I've got to get myself in order here. Sorry. At the time, blasphemy, or infamy, they've all got an infamy. None of you know the Carry On movies, probably. But 5 instances, that's a fluke. How about 14? Still a fluke, right? So 14 cycles we could go back observationally and do this analysis for. Referee said it's very subjective. After 2 years of battle, we need to develop an algorithmic approach to verify our observational approach, which basically means we need to write a code that can search through the data without human influence and identify the same features, right? Which are blatantly obvious and smacking you in the face anyway. But we'll do it because we're nice people and a little bit aggravated, okay? So we go back and determine this thing. We also then say, well, can we use that technique to determine when the next terminator will occur? And I'll tell you that's been a pain in the ass. And then we'll talk about how the separation of the terminators gives you an idea. And this is something I forgot to mention when I had my crazy slide up. So I'm going to pivot back for a second. All right, this one. Okay. You'll notice that cycle 24 is smaller than cycle 23. Okay. So this is 24. This is 23. Our conjecture was that the further this termination point goes to the right, the Hale cycle that belongs to 23 eats into 24, right? So it's all about cancellation. And the longer you cancel for, the lower amplitude 24 could have. Now, if I pull that back in time and say there's less interference between cycle 24 and 23, cycle 24 is going to go up, okay? And there may be some really crazy shit as to why cycle 23 continued on in time, because it was way longer. It was 13 years, right? It's way long. But cycle 24 was pretty short. But so the idea here is that the interlap, the overlap between these Hale cycle bands modulates the shape of the one to come, okay? Okay, so I'm going to go back to here. So I'm going to use this data to investigate that behavior, right? And so now we're going to look at maybe some of you that are expert. I'm sure some of you have worked with a lot of time series analysis in your lives. And whenever I see someone analyzing sunspot data or a Fourier transform, my head explodes. Why would that be the case? Well, Fourier transform has fixed phase. Bad idea for non-stationary time series. The Hilbert transform, so which just brings me to my second dead white guy, David Hilbert, was designed to look at non-stationary time series. And in fact, in algorithms in things like this, my watch, to detect arrhythmias and things, is an on-running Hilbert transform, looking for asymmetric heart rhythms. Okay. So one of the things we did with this is a flash of brilliance from one of my colleagues, said we should use the Hilbert transform to identify the peak rate of change of the time series. So if the sun goes through a step function in multiple measures, will the Hilbert transform be able to pick it out? And so we applied the Hilbert transform to F10.7 in the top plot. So that's the black curve. Those of you that have used Hilbert transforms know that the outcome is two functions. One is the amplitude function, so how the function of the set of base functions varies with time, so the amplitude, so how much it wiggles around. And then the second one is the phase function. The phase function just shows you how the phase of the signal varies with time. And so they're represented here in the top two plots by the red curve and the black curve. And what you'll notice, and I have not effed around with this, this is the legitimate data. So these dotted vertical lines are the same lines that have appeared in all the other plots before. What do you notice? One, the Hilbert transform amplitude function goes through a peak there, and the phase flips. Okay? Uniquely at the terminators. Okay? So now we kind of have our algorithmic approach to doing this. And so what you've got is like, you know, I've got F10.7 here and also the hemispheric sunspot number. You'll notice, you'll see places where it goofs up. And where it goofs up is actually fascinating. And it tells us something really important. The other thing you'll notice, that the phase function isn't flat. So it's not a straight line. So look here, boom, see this guy? When does so we, in spectral analysis, we call that a knee. And it's usually indicative of the physics changing, right? When did that happen? If you look at the apex of that knee and look at other knees in the data set, October 2003. What happened in October 2003? Anybody know? Save that one for later on. As people Google off Googling furiously.
Badly, yes.
What happened October 2003. So Hilbert transform methodology was used to verify our analysis, but also to extend back in time. So there's features, and I'm going through this really slow. I hope nobody's got to rush off. All right.
This is good stuff.
So now we're looking at longer time series. So we're going back, not to Galileo's data, because that data is not super reliable, but we go back to when the data is truly becomes consistent. So that's in the late 1740s. Okay. So that's a long freaking time. Okay. So in the black dots in the upper curve are the daily, so those are the monthly sunspot numbers. I think mostly determined from the either Locarno or Zurich time series. The red is that smoothed over 13 months. Don't ask me why it's 13 months. I think that's just hodgepodge. And then the blue line here is our trend on the data. So we've used a 40-year rolling window through the data. This is called an R-Lewis statistic to determine what the trend is. Because what we identified actually was when the Hilbert transform messes up, like here in 1970, it's because we've actually over subtracted the trend. So it turns out that this trend reduction actually takes away these F-ups with the Hilbert transform. Okay.
So Scott, the prize goes to Mike Walker for remembering a Saturday of an enormous CME back in October 2003.
Do you know why, Rod? Because I was coming back from the contest station after getting ready for CQ Worldwide, And it was a nice day. I was in a convertible driving through Northern Ontario, looking up and seeing the most amazing ever Northern Lights.
Yeah, so that flare around about Halloween, that would be called the Halloween storm.
Yep.
Was the biggest flare on record. Okay. Yep. So put your critical thinking hats on. This is for Mr. Howell there, right? Put your critical thinking. I don't think we've discussed this, although he might have read the other papers. Is this the tail wagging the dog? Why would the Sunspot time series change as a result of that? And then critical thinking experts, remember what I said about cycle 23 becoming very long, right? There may or may not be a pattern in all the long cycles. Okay. But what to think about right now? Here, jumping back. So here's our detrended time series in the second plot, amplitude function in the third plot. And I don't care about the amplitude function too much because the more rigid diagnostic is the phase function. And just to show how much of a math whiz I am, I completely reversed my previous strategy on you. So now I'm looking at zero crossings because I can set where phase equals 0 in the Hilbert transform. As long as I'm consistent, I can set it anywhere. Okay. And so I set it equal to 0 on February 11th, 2011, because I know a Terminator event happened then. Okay. And so you can see all of the crazy dots here, diamonds, are the 100 millihemisphere analysis of sunspot areas. And what you'll see is that actually it's not that bad. But now we can go a lot further back in time. We now have 24 Terminators. Okay, not just 5, not just 14, which are, just remember, are all coincidences, right? Just coincidences, right? Inconvenient truths, maybe more like, but coincidences, all. Okay. What does that pattern show you? So instantly, if you cross compare the bottom and the top, just by eye, this area around about 1800s, we call it the Dalton minimum, and it was the last grand solar minimum, right? And it wasn't even very grand. I would say it was kind of meager, right? Or kind of underwhelming solar minimum, right? But look at what the Terminators do during that phase. They get stretched out. And look at cycle 19, and here in 1950, look what happens to them. They compress. Okay. That gives you a hint that maybe our crazy intuition from 2012 wasn't that far away. Now we're going to do 2 experiments. I'm going to look at the Terminator, 2 Terminators. So again, I'm trying to measure how much the Hale cycles overlap with one another. Okay. So I'm going to use this measure of Terminator separation as identified by the Hilbert transform. And I'm going to compare it to 2 things. I'm going to compare it to the sunspot maximum between the 2 of them. And then in the second case, I'm going to look at the sunspot maximum that's coming up. So it's actually a predictive tool. Okay. 2 experiments. Shock horror, the first one's complete crap. No predictability. 0, nada. Zilch. But what about the second one? I'd say that's pretty freaking good. The only thing wrong with it is this cross-hatched area right here, right? Because for those of you that are time series experts, you've probably realized that the Hilbert transform suffers from somewhat the same issues as the Fourier transform when it comes to looking at the future, right? Because that phase function varies with time and the amplitude varies with time, using it as a predictive tool isn't always the smartest thing to do, but we did it anyway, okay? And what it showed us at the time was that we thought that the Terminator was going to fall last year. And it looked so close on election day, I will tell you, so close, except for the fact that it was only the southern hemisphere that did it. So the south rose, right? The north didn't follow. And that's a whole different story, right? And for Frank, that's you and your south, dude, right there, right? So, but one thing you'll notice in this plot, and if I go back just for reference for solar cycle 24. Oh, before I forget. All right, so that was our original crazy forecast for cycle 25. So if it fell in 2020, we were within this box, this huge box. Within 68% confidence, we were inside this little box. That's pretty damn good, right? And you can see how that forecast varies with time. It goes down about 10 spots a year. If I look at where the consensus forecast is about 115, right? I'm chuckling, right? Because you couldn't get more of a brilliant test for physics than this, right? If I draw my straight line across to where that cuts through the curve, solar minimum would have to continue for another 3 years. Anyone want to place bets on that happening? Maybe not. But I'll draw reference to you. The same experts that built that prediction also screwed up cycle 24 and also screwed up cycle 23. Okay? This regression analysis nailed 24. Like, it's literally sitting right on the freaking curve. Okay? And actually it does a really good job with weak cycles. And why is that? Get to that in a second. So, Hale cycles overlap and interfere. This is our hypothesis, right? We are screaming madmen, okay? And women, okay? The Hale cycle ends. The end is a trigger. The death of that one cycle gives rise to very rapid growth and activity on the upcoming cycle. The corona, so the outer atmosphere of our star that is less dense than something that's really not dense, right? But very active, reacts like crazy to that change, which is why you see F10.7 jump up, right? Hilbert transforms will give us a chance to observationally determine what's happening. And yes, a termination event of cycle 24 is pending. In fact, may be happening right now over this rotation or the next one, okay? Watch out. It's getting close. I'll get there at the end. But just to verify this, because again, now 24 coincidences, right? We now have 24 coinkydinks. One of the ways that we could go back and demonstrate the power of our regression was by hindcasting the data, okay? So if you look at this, it does a great job with low cycles, but it does a really pretty crappy job with high cycles. Why? Because there's not that many of them. So at the lower end, your statistics aren't very well bound, right? So what we're saying is that for every year, this thing drops by about 15 spots. So we're still in the Whopper range, okay? Are we ready for a large sunspot cycle? I would argue, no, we're bloody well not. The power grid people will tell you, I don't believe the power grid people, okay? Because the cognitive dissonance and Upton Sinclair and all that stuff, right? We'll see the cycle grow. So cycle 25, we've already seen the preliminary spots from that. It will grow like crazy and will ramp up like mad. One of the things that my buddies have been looking at is how the Earth's atmosphere responds to that and the oceans of our planet, which are also, that's a very interesting coupled problem. And so I'm going to get to kind of where we're at. So as I hinted about election day, it was looking pretty good. And then that happened. Okay, the sun is the breaker of models, right? It's kind of like trying to forecast the weather, right? You get too many observations, they're too high quality, the models aren't good enough, and so your chances of getting it right are pretty actually small. Same for the sun. But if you can't do that for the sun, why the hell would you think you can believe you can do it for something that's 30 light years away? Or 30,000 light years away? Give me a break, okay? So remember what we're looking for. right? We're looking for this stepwise, we're looking for a stepwise drop at the equator and growth at mid-latitudes. Like I said, that this is like a prairie fire, right? So it's actually a longitudinal effect too. So when the sun goes through this transition, and just to mess with you, I've flipped the color scale. I apologize. This is in reverse. So look at what the equator does. So the equator is activity, boom, goes into a lull. It drops by 50%, okay? Overnight, or within one rotation, overnight for the sun, okay? But look at the northern hemisphere. The northern hemisphere goes boom. This is a very rare epoch of time. This is the one single time in human history, 4 years, when we can observe the sun, all 4 pi of it, okay? Use this data to look at the longitudinal behavior, and lo and behold, yep, it starts off with one spot that is heating. After the Terminator event, it's strings of spots in each hemisphere, and they last for rotation after rotation. So there is a canonically different magnetic environment on the star after that event. Completely dramatic. If I go back and look at my old data, right, it looks significantly, this is where you get to see how crappy it is, because there's only really 4 images a day I can use for this analysis. Unlike this one, where it's thousands, okay? So you can see the same thing happen. So this is not a fluke, but this is what we're watching for, okay? So here we were in late 2020. It's the same plots. So left-hand side, northern hemisphere, right-hand side, southern hemisphere, in the middle, the equator. And remember how I said that the south rose first? Well, there's your activity in the south, okay? If I go on a little bit in time, and remember what I'm watching for is this green turn into red, right? And then this red turn into green, basically, in this color scale. Go on a wee bit further in time, a wee bit further still, not quite there. Not quite there, but there's telltale signs that we might be really, really close. And this is it's literally a switch we're looking for, remember, right? I update this data every 3 days. So there we were also. This is, I think, end of May. So here's my cycle 25 bands. Guess what? They've been visible since 2017. We've been tracking them since 2012. Okay. But nobody believed us. But that's okay. It's just science, right? Anyway, and in the bottom half, we slice through this thing at different epochs in time. So the purple here is 2016, 2017. So you can go back in time and say, yep, 2 very pronounced activity bands close to the equator. And then you can see, so basically these functions illustrate how peaked the cycles are. And you can see the bands of cycle 25 quite beautifully in this plot, except for the fact that the equator needs to drop by about, it needs to come down to about 1 before we're sure that it's happened, okay? Changed. That's over the course of a week. Actually, it's over the course of a few months, but it's averaging the living crap out the data. But you can see now that that cloud that's here is gone. So we're really in the final embers of cycle 24. So cycle 24's final embers are present right now. And if you look back to 2011, which is over here, you'll see it's about the same density. And then almost overnight, it just goes. If I show that plot a little bit more, you can see this cloud. It's kind of dwindled. Not a lot, but enough. You can see the growth in the mid-latitudes is really trying. Oh, and the other thing I forgot to point out, who can see cycle 26? Give you a hint. Look at 55 degrees latitude. Do you see the bumps? There's little bumps here and here. That's cycle 26. Okay. You think I'm absolutely mental. Don't you? Actually, that wasn't a question. That was a statement. Okay. So Just other analysis that shows the same behavior. So this is again is my old spacecraft. Been analyzing this stuff for the last 24 years. Here, and this is looking at just at the morphology of the sun's corona. Okay. So the sun's corona does the same thing. It has bands that come in from high latitudes towards the equator, which then die, and then activity springs up at mid latitudes. Okay, so there's a whole bunch of different phenomenology that shows the same. Here, the very interesting thing we learned, and I haven't showed you this yet, that the Terminator event that happened in 2011 gave rise to the event that reversed the sun's polar regions. And I'll show you that in a few slides if you're patient enough with me. But that happened all 16 other times that we can catalog this, right? So when the Terminator happened at the sun's equator, activity sprung up at mid latitudes, but then the polar reversal process started at high latitudes. So you can think about this when it happens at the equator, it's like almost like a tsunami. The entire environment inside the sun changes, which then drives the polar reversal. It's the most bizarre thing ever, okay? But it happened 14 times, but I guess there's still 14 coincidences, okay? Just remember that. This isn't real. This can't be real. But what the point of showing this plot is, see what's brewing at 55 degrees latitude? The polar reversal push. They call it the rush to the poles because I remember they're not very imaginative, right? So if you want to visualize, sorry. One of the other things that happens as a result of this is that the corona, remember how I said that the corona switches on and switches off? Well, in halfway through 2020, the coronal emission, the magnetic field shrunk to smaller scales. And so the corona that we've been looking at mostly in this analysis at about 1.5 million degrees is not energized anymore. And so it becomes dark. And there we have it on the left-hand panel. Do you see that dark band in the sun's corona? That's because there's a civil war going on there with cycle 24. Okay? It's killing itself. And as it kills itself, it shrinks to smaller and smaller scales, right? So the field goes from this global scale and shrinks down and down and down until it's just small little bipoles, little bright points that are battling with each other. The interesting thing here is if you look at the cooler corona, so this is 1.5 million degrees on the left. I know these numbers are kind of mind-blowing. On the right-hand side, it's only 900,000 degrees, only, okay? You'll notice that that patch doesn't exist, right? It's actually filled in. This is identical data, same time frame. Global field is not populated. Local small-scale field is populated, and it looks mushy, right? It looks blurry. And it's because the magnetic field's all at the smaller scale, okay? So how the sun's magnetic field evolves happens across multiple scales at all times. So now we're going to come back up to compare forecasts, okay? So as I said, the contrast couldn't be greater between us and the consensus. The thing that interests me most about this is not the fact that I don't really personally care about the prediction. I care about the physics, because this is if we're right, this is a paradigm shift in how you understand what the sun's doing, and by result, other stars. Okay, because if the sun's doing this, and remember, the sun, according to astrophysicists, is a boring star, right? Right. I wouldn't complete my thoughts on that. So if I go back to my buddy Chris in Austria, he uses this plot to taunt me on a daily basis, okay? So here's a plot that's generated at this website, so you can all follow this for yourselves, of Chris's tracking of the cycle, the forecast. So the blue curve here is the consensus panel. The red curve is ours, the high end, so the one with probably the wrong Terminator date in it, which needs to be revised once the Terminator actually happens, versus the average, the green line. And it's not doing too bad. we said by probably the middle of 2021, we could tell if we were on track or not. It's not too bad. Random shit can happen on the sun, unfortunately. How does that look if I update it to today? Oh yeah, still going. So we're just going to watch this. I'll pull my hair out as time progresses. So
can I ask you a question on that, Pat, on that last slide?
Yeah, sure.
So you mentioned that this your red line here was drawn with the Terminator from back in November, assuming that was a Terminator. If you were to update that and say, let's say, for example, the Terminator happens today, ignoring the fact that you actually think it's happening today, maybe. Just for statistics purpose, how does that change this red line?
It pulls it down towards the green.
But not below the green.
Oh, I don't think it will go below the green.
Okay. Because if I'm understanding correctly, the later that Terminator happens, the more it interacts with the next coming cycle, and it would bring everything down. But it's not good, but not dramatically, just a little bit.
For every year, so if you follow the regression, for every year that passes, the forecast spot number goes down by about 10 to 15.
Okay. For every year, and it's only been about, what, 8 months now?
Yeah, so we're not so far off. But I mean, I tell you, the second that we prove that it's happened, or sorry, validate that it's happened, we'll be sticking our middle fingers up everywhere.
I like your attitude, by the way.
Oh yeah, I'm way too competitive to be a scientist. I'm sorry, but
is there a bet on? Is there a bet on this, Scott?
There are several bets on this.
We'll be linking to the Vegas site sometime soon. Yeah.
That and very expensive bottles of whiskey. I actually want to, I was trying to encourage my friend to take a bet on liquid natural gas. But anyway, because of the other elements of this work, that you can make a lot more money out of speculating in the futures of natural gas. But the thing to note here is that also, well, I guess I'm relatively happy. I look at this on my phone every morning and I'm like, okay, I'm not that mad. So it's tracking pretty well. So, even if it comes down to green, it's still not the blue one.
Mm-hmm.
And just watch when the Terminator happens and cycle 25 takes off, because it'll be quick. Watch all the people that made that forecast changing their models. Dirty secret. I think we call it tuning, right? Some people call that cheating. But anyway, we'll go on. So conclusions. You've learned a little bit about the sun's hail cycle. And just to show you, remember how I was rambling on about 55 degrees? Do you see this pattern that's going on in this animation? Do you see the green dots? Those are things called prominences. So the sun has these features that are very prominent at the limb, right? Prominences, get it? Okay. When you catalog them over time, and the catalog of those bad boys goes back to 1860, to the very dawn of plate photography, right? People were publishing papers in 1903 on this repeated behavior that they were seeing in prominences. 1903. There's a dude called William Lockyer who had a pretty famous daddy who was writing papers about these prominences. I'll show you that in a few slides. But anyway, so you've learned a bit about the Hale cycle. It's recurrent and robust. We see that. It actually, the 22-year thing is pretty loud, solid. The bands of the Hale cycle have a definitive end. We've called it the Terminator. Maybe we should have called it something else. My buddies and I have a call sign for it. We call it Arnold, right? Shock horror, right? There's another joke that goes with it. Remember I told you that there's something that happens at the other end to signal the ingress into solar minimum. Well, there's a bit of a conundrum there, right? Because what came before a Terminator? Was it a James Cameron or a Kyle Reese? So what do you call that one? Right? And then it's chicken and an egg, right? So anyway, philosophical debate to ensue. The Terminator rapidly triggers growth at mid-latitudes and also at high latitudes within about 1 solar rotation. I haven't really gone into that data in a lot of detail today, but I have other slides to show you just how bloody abrupt that is in terms of radiation, okay? We see a rapid jump up. The 24 hypothesis was that the hail cycle bands interact to modulate sunspot activity. I'm not sure that that's, at least from my perspective, couldn't be more solid. Not the case in my community, okay? This is completely third rail physics, right? Don't piss on the third rail, okay? Terminator separation as it stands is 10.25 years. And if that happens, we'll have a larger than average cycle, okay? Maybe reaching into the top 5, because remember I told you that it underpredicts big cycles, right? Because there's not been many of them. And so, you know, one of the really cool things about this work is that these Terminator events actually allow you to form a cycle, a clock for solar activity and geomagnetic activity and a host of other things that allows you to make sense out of climatologies a little bit, if you think about that. Because one of the reasons that we can look at the average day at the end and start of July in Colorado is because of the regularity of the sun's orbit, or the Earth's orbit around the sun. I nearly got it wrong there, right? And it's because of that regularity and the seasons that are induced by that we can look at averages. Now, if you use the wrong clock to average activity, you're going to just get claptrap. But if you use the right clock, things start to make sense, don't they now? Okay, so with that, I leave you with the question here before I go on to my last few slides that show you how we apply that stuff, okay? The question is, are we ready for a cycle that is larger than average? My conjecture is no. Simple. Nope, we're not. Based on all my experience and the people I talk to and the people I've talked to in the recent past, hell no. The people at the place that does all the weather forecasting, definitely not. Okay. Now, third dead white guy, Charles Cree, developed a piece of methodology called the superposed epoch analysis. In that, remember how I said about the Earth's clock, the Earth's rotation orbit around the sun? That's a clock. That's 1 year. Okay, well, it's 364.25 days, but it's a year. Okay. Cree tried to use, he developed a statistical analysis to try and collapse data on top of itself to understand if there was indeed periodicities in sunspots. Okay. But that technique was kind of thrown away by the astronomers because it didn't really work, but fully embraced by the meteorologists and weather people at the turn of the last century, right? Because it allowed them to stack up and look, oh, what's the average weather look like in London in January? Shit, that's right. So let's look at what it does to the sun. So now here's my full 160-year record of, remember these things, prominences? I only showed you a snapshot of them before. Look what they do. So so this is the butterfly diagram in gray in the middle. And in this case, I'm only plotting the highest latitude prominence in each hemisphere. So red is north, blue is south, and it's from 3 different observatories spanning the 160 years, okay? It's a pretty incredible record. They're all completely consistent with one another. Tonks along, Terminator happens, boom, goes off to the pole. Tonks along, Terminator happens, goes off to the pole. At the same time that the sunspots are born at mid-latitudes. 14 coincidences, right? North, south, middle, all of it. 14 coincidences. What happens if I use this as a tool now? So this is contemporary data. So again, this is my coronal morphology analysis that I showed you earlier, very briefly, from 24 years of data. So, and on the right-hand side, just for fun, this is a measure of the difference. Oh, hold on. I've got to get this right. A measure of the difference of the rotation of the sun's interior. Okay. Okay, so they measure using the seismological techniques the rotation of the sun's interior. And the red and blue here isn't magnetic polarity, it's speeding up and slowing down. Okay, so you're basically seeing circulation. Look at the patterns. Do they look vaguely familiar? So you've got the thing on the outside of the star, all the magnetic field stuff doing all its magic. And it's all being stirred by something on the inside. Maybe the process that makes the magnetic field. Maybe. Okay. So if you look at that analysis in time, you'll see that you'll get a rough idea that the pattern repeats itself. Okay. This chevron-y like pattern that comes in from high latitudes. Now, if I animate that and then show you the average, now the apologies that these go through pretty quickly. So I'm basically taking Terminator plus or minus 11 years and just moving it through my data one Terminator at a time. Okay. When you take the average of that, guess what? It looks like the same stuff. But that's only 24 days. That's only 24 years. What happens if I use the green line data that goes back 70 years? Goes back to World War II because they were using it as a proxy of solar activity for radio propagation during the war, right? If I do the same analysis on that, guess what? Same thing. Right? So now I've got 70 data. Remember those 14 coincidences? Right? So what it basically shows you is that solar activity is collapsing onto itself if you use the Hale cycle as your clock. Now, if I use my entire 160 years of prominence data, guess what happens? Same thing. Stack it all up. Boom. But what if I do it just with sunspots? Oh, there's a shocker. I only get half the pattern. Damn it. Or not, damn it. What's it telling you? Right? But look how beautifully this, when you use the Terminator, the sunspot patterns collapse on top of one another. But it's only half the pattern. Okay? If you were trying to solve a problem and only using half the data, how well do you think you would do? That again is a statement, not really a question, right? Back at the dawn of time here. If I look at the last 3 solar cycles, what's the sun been doing? Going down.
Right.
So as the sun's been becoming less impactful, the interest in research in it has been going down.
And I think there's an obvious linkage that just about everybody in the crew is thinking of right now, which is, okay, it's been going down, it's been going down. Oh, by the way, we're putting up all these constellations of spacecraft on there. What happens to all these spacecraft that have been engineered for the last 10 or 15 years, bumping into a world in which
the thermosphere is a little bit more dense?
Yeah, like basically, are we putting a lot of stuff at risk?
So this is where I can neither confirm nor deny that I may have been working with people on forecasting that stuff.
Probably insurance companies.
or manufacturers.
Yes, exactly.
Because on both ends it's a cost problem. So you can ride that out if you put enough fuel on the bird, right? Because you can just, so flash heating in the atmosphere inflates the thermosphere, which then drags the satellite down. Okay.
Right.
So you can either lose them or if you've enough fuel in them, you can just boost them back up to their orbit. But you can only do that for a finite amount of time, depending on how much fuel you have, which is a launch cost. And if you're launching 60 of these at a time, do the math.
Yeah.
So they always cut the margin, right? Always. And their experts have barely been telling them that activity is going down. And it will continue to go down. Now, I've got another friend who's an expert in space junk in Southampton, in England, and they have one of the world's premier labs on space junk and space debris there. And I gave a version of the much longer, actually, believe it or not, version of this talk there. And we got into some very heavy discussions about how the sun's going to actually help some of the space junk problem just naturally. If this happens, but
help in the long term, but also maybe create some unpredictability, as we've seen in the last year with Chinese deorbits, right? We need to be able to predict those, and we need to be able to understand exactly, well, we're never going to know exactly where they deorbit, but at least what the probabilities are.
How many cows are going to be killed by fallen spacecraft? Did Skylab not take out a cow?
Yeah. Exactly.
Yeah.
Hey, Frank. Oh, okay. Go ahead. Go ahead, John.
I got to ask Scott this before he disappears. So both solar processes and Earth climate processes are not only complicated, they're very complex.
Coupled.
Yeah, well, yeah, but I'm trying to stay away from a climate change discussion. I want to know.
Very wise.
I'd be happy to have one, but that's not today. From an objective scientist point of view, how would you compare the complexity of trying to understand solar processes versus trying to understand Earth climate science? Like, are they comparable complexities?
Yes. There's one difference, however. We live in that atmosphere, right?
Yeah.
I mean, it's all about the integrity of your measurements, really, is the challenge there, right? From the Earth side perspective. From the solar perspective, we're 94 million miles away, right? And so we're actually more crazy. It's more challenging because it's also remote sensing.
Yeah.
So you're only counting particles or photons, right? You're not measuring chemical compositions. You're not, well, you can infer them, but it's all inference. And so it goes back to remote sensing science versus, in situ measurement. And so in climate, it's about the integrity of the measurements that you have to make your inference. And from our world, it's the quality of the remote sensing capabilities that we have. And like I said, the mind-blowing thing for me when I did this analysis, so two things. One was when I was way further down the line looking at these prominence things and seeing that people had published papers with these patterns in 1903, right? That's a WTF moment from me, okay? Even in Italian. I don't know what WTF is in Italian, but I was saying it, I'm sure. Also, I discovered when I was 95% of the way through the paper that it was published in 2014. As I was saying to Rod before we come on, I think I said this to Frank too, the original version of that paper was submitted in the fall of 2011. And it took that long to get it published, but it also quintupled in size in that time. Okay. What I discovered literally just prior to submission of that paper in 2014 was that someone had published pretty much the same analysis and drawn the same conclusions in 1988. The only thing they didn't do was link the pattern that they saw, the sunspot cycle. It's the only bit they didn't do. And it wasn't just one person. It was a group of very, very dedicated professional solar physicists at the world's major solar observatories. The timing in 1988 was just at the very dawn of high performance computing, readily accessible HPC. Their work in my community is like a dirty secret, right? Everybody knows about it, but no one cites it. And so this is, remember I said at the start, I'm standing on the shoulders of giants. A lot of those people that appeared on that first slide, I'm not letting go of this as somewhat of a tribute to them, because they kind of figured it out. Kind of. They didn't go as far as we went. But remember how I said that my old mentor probably knew what I was going to find? He and I still haven't had that discussion yet.
So thank you for your answer. I you know, while I'm fascinated by sunspots, I'm equally fascinated by your discussion of the scientific process. So thank you.
Yeah, I don't try to be. I try to walk you through the logic the way I see it, right? I mean, I use the data. I'm not cherry picking it. I could put anything on this chart, right? So,
Scott,
in fact, I have an intern this year who's building a website so that people can do this exact analysis for themselves using exactly the same data, okay? So the idea is to do that from a standpoint of reproducibility, that my colleagues can do the same analysis.
very good.
No, there's sorry, go on, Rod.
You'd mentioned instrumentation, remote sensing, that kind of thing. What sort of spacecraft are you using now in terms of what are the most useful spacecraft to get some of this data?
Well, I mean, so the big one that we're kind of excited for this time is solar probe. So the Parker solar probe, because when the Terminator happens, the thing that we didn't have really high quality in situ measurements of the heliosphere, right? So if you think about it, the way I look at the solar system is like a huge jellyfish, right? And it expands and contracts. So as the sun's magnetic field expands and contracts, so does the heliosphere, right? Has to. Can't not do it, right? Has to. And what I would love to see is if and when the Terminator happens, what happens to the interplanetary magnetic field as the tsunami? Because the tsunami is not just contained within the sun, because that sea change that happens in magnetic activity absolutely ripples out through the heliosphere, right? So what I'm really interested in is, what does Parker see as this thing rumbles past it, right? That's what's different this time. SDO is a beautiful spacecraft, taking super high quality data. Can I tell you the thing that I really covet? So what I really want, and I've been pushing this at the kind of national academy level, is I want 4π observations, right? I want to understand this thing. Hold on, go on, get back to here. Well, this thing for sure, but it's most easily demonstrated in this.
Right.
What's going on at 55 degrees latitude?
Mm-hmm.
Why does it repeat? That's where I think the sun's magnetic field's being formed. So if this is my Livingston and Stanley moment, right? There's X marks the spot right there. Now, can we fly something up to high enough latitudes to observe that flow, right? So the problem is from the equator, when you get up to about 55 degrees and you're using the Doppler effect to measure the flow, the line of sight is killing you. So you actually need to fly up there. So Solar Orbiter, so the other probe that's out there right now, new one, will go up to about 30 degrees latitude, but in about 8 years, right? So it slowly kicks its latitude up. it may not be high enough for long enough to see the flow.
Right.
So what I want is something up to see that, so that can we actually see cycle 26 or 27 forming, and then see its march, right? Because that would be proof positive of what we're talking about.
Okay. And Frank has been very patient. I'm going to get to him right now.
Scott, you know, I really just have a simple hand gesture to describe my impression of your talk. It's a thumbs up, friend.
Yeah, thanks, Frank.
Comment in general for the hams, because, you know, we're users of this. What is so exciting about this in science is that it's science at its best, because it's a contrasting paradigm. Now, Scott and his team didn't just get a new toy, like, say, the Hubble Space. You know, we got a new telescope out there, and we can tell more about Saturn than we ever could with the heat damaged optical images. So it wasn't just that they got a new toy. It wasn't that one or two of his team extracted some esoteric statistical method to model sunspots. No, it's a new and moving theory they're developing that is different than the consensus model is based upon. Now, those of you who like Albert Einstein may remember there was a day when the literate world waited until these two people went out to, Scott, you'll have to help me, somewhere in Africa or South America or somewhere.
Argentina and London.
Right. To collect pictures of sunspots, because it would go up or down, kind of like the graph Scott pointed out of where the consensus projection is, where his team's projections are. And we're going to get what a lot of people are going to say, oh, great, or I told you they were wrong. So we're going to get some kind of definitive evidence, more or less. And yet the thing is, I've gotten to know Scott. He's not starting with an answer and trying to find data to support it. And having been on panels at NSF and NIH and panel manager at USDA, panel managers are like the referee in tag team wrestling. Don't hit them too many times below the belt, you know. And so having been there, people who come in from the consensus world tend to want to protect their turf. It's not an electronic circuit, folks. You know, we can model this out with SimSmith or something, and that's one thing. These are people operating in groups. And so one of the things that happens is when you have a contrasting paradigm, you know, there are a lot of sparks on that wheel as you try to refine that instrument. And it's kind of tough getting funding, because you're going up against folks who are well positioned, and they're the ones that we think of. Just like we read the ARL antenna handbook. Oh, propagation is based upon sunspots. And then we worship and dip and we go along those lines. What Scott's team is doing for us is a new paradigm. And that's one of the reasons why I just find it so terribly exciting. It's one of the most exciting things, like the sizer stuff in genetics and all the breakthroughs that have come there. I've encouraged Scott that in a few years, I want us to promote his new book with his team called Following the Sun, Breaking the Cipher to the Rosetta Stone of the Galaxy. He has promised that when his projections are shown to be the ones of preference because of the data, if that turns out, he's going to come back to the ICQ podcast in video with a kilt and dance a set of Scottish jigs in Colorado that we're going to feature on that podcast. Shameless promotion, Rod.
You heard it first here. So with that, I'm going to thank Scott, and I'm going to end our YouTube recording. But Scott, it was amazing. Thank you for the time you've taken with us. And yeah, stick around for a few minutes.